All right, this is day 30. We're talking more about hypothesis testing and confidence intervals, and today we are focusing on comparing multiple quantitative variables. When we started talking about hypothesis testing last week, we were working with a single population, and we started off with categorical variables. So, as a measure of a categorical variable, we talk about the percentage of the population that falls under the category in question. So, for a 1 proportion z-test, a typical null hypothesis would be that the population proportion, so the percentage of the population that meets a certain criteria, is some predetermined value. The next time when we did quantitative variables, again working with the single population, for our one sample t-tests, our null hypothesis was typically that the population parameter, so this population mean, was again some predetermined value. Last time, however, we started working with multiple populations. So rather than comparing the population's proportion to some set value, we were comparing two population proportions to each other. So typically the question here is there a notable difference between these two populations? In the example I used last time, we're concerned with what percentage of candy is green, and we're comparing the population of M&Ms to the population of Skittles. So if P1 is the percentage of M&Ms that are green, and P2 is the percentage of Skittles, our null hypothesis would be that the two percentages are the same, and we typically are investigating to see if there is evidence that the two populations are in fact different. So a typical alternate hypothesis would be that these two values are different than each other. Today we're working in this lower right-hand quadrant. We're working with multiple populations, and we're doing quantitative variables. So here we're actually getting two hypothesis tests for the price of one. An important consideration we have to make is whether or not our two data sets, our two distributions, are paired or not. And more on what exactly that means coming up. So we'll certainly talk more about what I mean by paired in a little bit, but just to give names to these tests, the first one is the one that you would expect given some basic pattern matching. We're now working with two samples, and it is quantitative, therefore it is a t-test. There is an implied unpaired tag on this test, but we typically don't bother saying that. When we say two sample t-test, it's usually implied that it's unpaired. Again, I think we could probably guess what a typical null hypothesis would be here, and that's just that the population parameters for two different populations are in fact the same. So our null hypothesis is that the average of population 1 and the average of population 2 are in fact the same thing. Again, if our data is paired, we'll do something a little bit different. So when we talk about two populations, often what we mean is that they are in fact two separate groups. Say we're measuring something about Swarthmore students versus Haverford students, or cats versus dogs, Skittles versus M&Ms, etc. And in those cases, we could identify some parameter, so the average lifespan of cats versus average lifespan of dogs, or the percentage of M&Ms that are green versus Skittles. And then the questions that we ask are typically, is there evidence that these two populations are different with respect to this given variable? So each of those, I would say, are examples of unpaired data sets. Let's take the cars versus trucks example. If the variable that we're measuring is the fuel economy, let's say in miles per gallon, we could have some data sets of cars and some data set of trucks. And what we're concerned with is, what is the average fuel economy amongst the cars compared to the average fuel economy amongst the trucks? This is unpaired in a sense because each row doesn't necessarily mean anything. Car 1 isn't related to truck 1 in any way. This is in contrast to paired data sets, which often happen when you have a single individual doing something in different ways. All right, so if we have a similar example, we're again interested in fuel economy, but now the question isn't between the population of cars and the population of trucks. The question is, between the situation where we're using these snow tire chains. So if you've lived anywhere where it snows, you typically have seen these chains that you literally put around your tires. It gives you extra traction. The reason you don't always have the chains on there is that typically it's going to reduce the fuel economy. So if we have a question like, does using the fuel chains actually reduce fuel economy, we can run a hypothesis test, and it might make sense here to use a paired data set. And what I mean by that is we might have our first car go and measure its fuel economy both with and without the chains. Maybe we'll see something like this. Again, this might be in miles per gallon. And then the same type of thing is true for some rest of the data set. So again, the important part is that we are comparing a single data point in one group to another data point in the other group. And because it's the same car, this is going to help us isolate the difference between the two groups. So typically we will use paired data sets when we're testing something that it's possible to have a single individual do it in multiple different ways. This typically gives us a more direct comparison, helps us make a stronger conclusion. That said, it's often not possible to set it up this way, just depending on what type of question we have. Okay, let's first talk about the unpaired example. We'll use the same example that we were just talking about. We are concerned about the fuel economy between two different groups, the cars versus trucks. So if mu1 is the average miles per gallon for cars, where our population is all the cars that are out there, and mu2 is the average miles per gallon for all of the trucks that are out there, our question is, do we believe that mu1 is bigger than mu2? Again, I keep saying this, but it's so important. Whenever we use mu, we're talking about a population, in this case, the big picture of all cars or all trucks. We're averaging the fuel economy across the entire population. To answer this, we could literally measure the fuel economy for every car and every truck in existence. That certainly sounds not feasible. So instead, we're going to take a sample, and the question that we'll ask is, does the difference that we see in the sample give us enough evidence to say that, hey, these two populations as a whole are in fact different? Or was this difference maybe just due to random chance based off of the sample that we took? So like last time, hopefully this is starting to feel familiar. We're setting things up in virtually exactly the same way as we've set them up in the past. The only difference is in what exactly we're measuring. Okay, so let's say that we're actually running this. We go out and we find 10 cars, so we do a random sample, and let's assume that these 10 cars form a representative sample of the population. We also find 8 trucks, and for each of these 18 vehicles, we measure the fuel economy. So we measure the miles per gallon it gets, and we look at the distributions for each of these. So there's certainly more information in the distribution. Maybe it's indicating something that's bimodal or skewed or something like that. But the piece that we particularly care about, the only thing that we're actually talking about, is the average. So what we're going to do is we're going to take that sample of 10, so 10 data points, and we're going to find its average and then also its standard deviation, because we'll need that later. So as we can see, with our two different samples, sample 1 had a larger average than sample 2, which on its face certainly seems like evidence towards this alternate hypothesis, because 1 is bigger than 2. But the question remains, is this enough evidence for us to substantially be able to say that yes, the entire population follows this trend as well, or is this just a superficial difference? So as always, that's the question we're trying to answer. Again, as usual, to answer this, we are going to assume that the null hypothesis is true. So we're saying, if this null hypothesis is true, how unlikely is it to get a sample that looks like this? If instead of comparing the fuel economy between cars and trucks, we were comparing between red cars and blue cars, if maybe we had a suspicion that red cars got more miles per gallon than blue cars, well, then we could do this process. We could take a sample of red cars and a sample of blue cars and compare those distributions, compare the averages. So in that situation, we're certainly inclined to believe that we wouldn't expect to see a substantial difference. However, we would still expect to see some difference. That's what this distribution is talking about. In the situation where the two groups actually are the same, how much of a difference would we typically expect to see just due to random chance? So this expected value is the middle of the distribution. If the null hypothesis is true, then on average, the difference between these samples should be 0. Just like last time, we can find the standard deviation of this probability distribution for the quantity x1 bar minus x2 bar by realizing that variances add. So we can take the standard deviation for the probability distribution of one of these, which would be sigma over square root of n, and square that, add it to the square of the other one, and then square root. That's where this equation comes from. As always, this standard deviation equation is great in the theoretical world where we know what the distribution of the fuel economy for cars looks like. If we somehow know what the standard deviation of that is for the entire population, since we typically don't know that, if we knew that, we probably wouldn't be asking these questions in the first place, we're going to use our best guess for what sigma should be. So again, rather than using the actual standard deviation for what this distribution is, we have to use an approximated standard deviation. That's where the standard error comes in. The standard error is an approximation for this actual value. And we're doing this approximation by saying that, well, the standard deviation of sample 1 was 15. Maybe that's a reasonable guess for what the population's standard deviation for the population 1 is. Often this isn't a great estimate, but since it's all we have, it's what we're working with. Whenever we estimate the population standard deviation with the sample standard deviation, that's our cue for using t distributions rather than z distribution. Degrees of freedom actually gets a little bit complicated here. Normally the degrees of freedom is the sample size minus 1. Since we've got two different groups, potentially with two different sample sizes, we found 10 cars but only 8 trucks, well, the degrees of freedom is actually going to be sort of a weirdly complicated formula. Please don't write this down. You pretty much never need to know this, but if you're really curious, this is how you would find the appropriate degrees of freedom in this context. For any question that I ask, I'll give you the degrees of freedom in this context. Alternatively, if you use R or a calculator or something else to do this t-test for you, then it's going to do all of this sort of behind the scenes. I'm not going to work through the rest of the details for this particular hypothesis test, namely because we've worked through questions just like this before. The one last piece that I wanted to mention is that we have another assumption that we need to pay attention to. So just like all of the assumptions that we had left over from the one sample t-test, for our two sample t-tests, we have the extra condition that we want to make sure that the different distributions are independent of each other, not only independent within their own groups. This is sort of a fancy way of saying we're assuming that we're not dealing with paired data. If we're dealing with paired data, we have to do something entirely different. Something different, you say? Well, while paired t-tests are certainly different than two sample t-tests, they're actually very similar to one sample t-tests. So let's work through the beginnings of an example for them. Again, we're concerned with the fuel economy, only now rather than comparing cars and trucks or red cars versus blue cars, we are comparing cars with snow chains to cars without snow chains. And the advantage here is that if we're actually running this experiment, for each individual, in this case for each individual vehicle, we can test both with and without, and that gives us this direct comparison. Because we're comparing this 30 to this 34, rather than the average of all of these to the average of all of these, it's typically easier to make a stronger statement. So the way that we'll work with the data set like this is we will just calculate the difference for each of the individuals. So then once we have this difference column, we're basically just going to do a one sample t-test on these values. So here's what I mean by that. We may say that for our null hypothesis, the population's average. In other words, with the population being all vehicles that are out there, the parameter that we're interested in is the potential difference, the potential increase in fuel economy for not having snow chains. As usual, our null hypothesis is that nothing special is happening. In this case, that there's really no difference between having the chains versus not. A couple notation things. If we're talking about this distribution, rather than calling its average x bar like we would for one of these other distributions, we're going to call it d bar for difference, and its standard deviation is going to be s subscript d. But other than that, we can just follow the exact same procedure as we would for a one sample t-test. The one caveat there is that we have an extra assumption, and this assumption is really just saying that we actually do have a paired dataset. This is, of course, in addition to the usual assumptions we make when dealing with t distributions. So I've been focusing on hypothesis testing so far, but all of this logic also applies to confidence intervals. So remember, the reasoning to do a confidence interval rather than a hypothesis test, or vice versa, all depends on the question that you're asking. If the question is there evidence that not having snow chains increases your fuel economy, then that would be a hypothesis test question. The answer should be yes, there's evidence, or no, there's not evidence. If instead the question that we're asking is, what is our best guess for what the difference is, then we want to use a confidence interval. So let's say that I ran this chains versus not chains experiment, and I tested a total of 10 cars, and saw that on average, not having the chains increased fuel economy by 1.3 miles per gallon. The standard deviation of this distribution, of this difference in fuel economy, happened to be 0.4. So given this information, what is my best guess? What do I think the difference in fuel economy is for the population as a whole? So for all possible vehicles. Well, given that this is all the information I have, if I had to guess, I would say it's an increase of 1.3, but there's certainly some uncertainty there. I'm not claiming that the population's difference is exactly 1.3, because what are the odds that we'll get the exact right answer? That said, I guess we're fairly close. We just need to calculate the margin of error at a given confidence level. So the margin of error, this t star times standard error, is the error bars on our guess. We think it's 1.3, give or take a certain amount. The t star comes from our confidence level. If we're using a 95% confidence interval, this t star for n equals 10 is going to end up being a little bit more than 2. And the standard error is the same standard error we've been using for our hypothesis testing. So if we actually calculate these things, by the way, this t star is less than 2, my bad. The standard error comes from s over square root of n, in this case 0.4 over square root of 10, and we see that our interval is 1.071 to 1.529. In other words, we are 95% confident that the actual increase in fuel economy for not using snow chains is somewhere in this range. Okay, so that finishes up our table here. We've talked about categorical and quantitative variables in situations where we have one population or where we're comparing two populations. Starting next week, we will be doing more hypothesis testing and confidence intervals, but dealing with data that is in a largely different format.